Okay, section 4.8, we're going to be graphing polynomial functions. So take out your calculators. If you don't have one, you can borrow one from me. And if you're at home and you don't have a calculator, I'm going to show you guys a website called desmos.com that I've mentioned in the past. So give you guys a second to grab your calculators. Okay, so in this chapter so far, we've learned that zeros, factors, solutions, and x-intercepts are all closely related. Virtually, they're the same thing. So the following statements are equivalent: zeros, factors, solutions, x-intercepts. They all really mean the same thing. So what we're going to do today is graph polynomial functions. We're going to do 3 examples, and then we're going to do one additional concept at the end called even and odd functions. The first polynomial that we're going to graph is in intercept form, but most of the polynomials that you guys will graph for your homework are in standard form. So this first one is kind of rare, but okay, how are we going to graph polynomial functions? We're going to plug them in our calculator. We're going to look for some points. We're going to plot those points. We'll use what we know about end behavior, like we learned in the beginning of the chapter. And then we'll graph our function, and then we'll answer some questions. This first example, we're just graphing. We're not answering any additional questions, but we will talk more about different things on the graph. So this first one, let's just graph. So actually, since this one's in intercept form, we already know where our x-intercepts are at. We know that we have an x-intercept at 2, 0, and an x-intercept at -3, 0. So we can, oh, my smartboard's off. All right, I need to recalibrate this real quick. Okay, so let's plot 2 points and our x-intercepts. Now, we learned previously that since the x plus 3 factor is raised to an even degree, we know that it's just going to touch at that intercept. And since the x minus 2 is raised to the first degree, since that's an odd degree, we know it's going to cross the x-axis at that intercept. So let's plug this in our calculator. Remember to plug in a fraction. You can just do 1 divided by 4, or if you want, you can do alpha y equals, hit enter, and you get numerator over denominator. That's a fraction. This is probably the easiest way to plug a fraction in to your calculator. So parentheses x minus 2, end parentheses, parentheses x plus 3, parentheses, squared. So once you get that typed in, hit graph. Okay, and you can see, like we said, the x plus 3 factor was raised to an even degree, so it does just touch there. And then we said the x minus 2 factor is raised to an odd degree, so it crosses the x-axis there. So we're going to get a couple other points so that we can just make sure we graph this nicely. So let's hit second table and just look for a couple other nice points to graph. We don't need any specific ones. I mean, maybe just get a couple in between the x-intercepts, and then we can look at our polynomial to determine the end behavior. So I'm going to drag this. Oops. All right, so you guys can make an xy table. All right, let's pick some of those nice points to plot, like -3, 0, which we already plotted, -2, -1, -1, -3, 1, -4, 2, 0 we already plotted, and 3, 9. So let's go ahead and plot those points. And then based on what we saw on the graph, we can just pencil this in. It doesn't have to be exact. There we go. Now we do know the end behavior. Since this is a 1 to 3rd degree polynomial, that's odd, so with a positive leading coefficient. So I think odd, I always relate it to a line, and it has a positive leading coefficient. So I think of a line with a positive slope. So you guys can see this does match what we think the end behavior should be. And again, we already knew that because we saw it from our calculator, but just to reiterate that end behavior there. And that's it, okay? So we graphed that. We got some points from our graphing calculator. This was in intercept form, so we plotted the intercepts, and we're done. But most of yours are going to be in standard form. So another important characteristic that we're going to talk about of the graph is that they have turning points. These turning points are where they change direction. So for example, this is a turning point here, and this is a turning point here. So that's where they change direction, where they go from increasing to decreasing, or decreasing to increasing. Now these turning points are called local maxes or local min values. So a local max, it's kind of like a vertex, but it's not the highest part of your function or the lowest part of your function, which is why we call it local. So it's a local max here and a local min here. And those are the turning points where the function changes direction. Now, when we actually talk about the local max and the local min, we want to know the y value, because I want to know how high this is and I want to know how low this is. So when I talk about the actual, so here, the y coordinate of the turning point is a local max, and the y coordinate of a turning point is the local min. So this is important. When you identify the local max and the local min, you're really just talking about the y coordinate. Now, when you'll see on the next example, when you tell me where the local max and min are, you're actually going to write it as an ordered pair instead of just identifying the y coordinate. So I know that's a little confusing, but once we do a couple examples, it will make sense. So the turning points of a graph help determine the intervals for when a function is increasing or decreasing, and we're also going to identify those intervals in interval notation. So increasing, decreasing, increasing. And the important part here, like we've done in the past, because we have done increasing, decreasing before, is that we are going to be talking about the x values, right? We're not, when we talk about increasing and decreasing, we're always going to be identifying x values. And you guys did really well with that in, I think it was chapter 2 in the past. So that's going to be kind of similar to what we've done in the past. Now, the graph of every polynomial function of degree n has at most n minus 1 turning points. So, for example, what that means is this is a 3rd degree polynomial, so it's going to have at least 2 turning points. This is a 4th degree polynomial, so it's going to have at least at most 3 turning points. So it's just 1 less than the degree, and that's how many turning points there are going to be. And I shouldn't say at least or at most. So if a polynomial function of degree n has n distinct real zeros, then its graph has exactly n minus 1 turning points. All right, so let's plug this function into our calculator. We're going to actually identify the x-intercepts. We'll identify the points. So I know I talked about the y-coordinate. The y-coordinate technically is where the max and min are, just like we've done in the past as well. But we're going to just write the local max and min as points. And then that's different than when we're going to determine the intervals for which each function is increasing or decreasing, I guess just the function. So the intervals are when we're talking about the x values. So that's going to be really important to keep separate. Okay, so let's plug this in our calculator. So we want x raised to the third power minus 2x squared plus x minus 2. All right, hit graph when you're done with that. All right, so we said since this is a third degree polynomial, there's going to be 2 turning points, and there are. There's one here where it goes from increasing to decreasing, and then there's one here where it goes from decreasing to increasing. It's kind of hard to see though. So there is a function where we can zoom in on that. You could either just change your window to zoom in here, or you can go zoom and then zoom box. So you can hit enter. And then you can make a box using your arrows. Oop, I think you have to hit enter again. Hang on. Enter, and then zoom down. Kind of a lot of clicking. And then I did not hit enter again. I just started arrowing to the right. I feel like I should have made my box bigger, but let's hit enter and see. Okay, I probably wanted to go a little bit over here more. So instead, what I'm going to do, I'm just going to change my window. So let's just go x min -5, x max 5, y min -5, y max +5. I think that's easier and less time consuming than using the zoom box function, but I just want you guys to know that that's available. Okay, and if we need to zoom in a little bit more, we can make our window even smaller, but you guys can see here's a turning point, it goes to decreasing barely, and then here's another turning point, it goes to increasing. So let's look at our table and graph the function first. So second table, let's get some nice points here to graph. All right, so let's make an XY chart. All right, so some nice points we have. We have -1, -6. We have 0, -2, 1, -2, 2, 0, and even 3, 10 is a nice point. So let's go ahead and plot those on our graph. And I forgot to mention the packet that the sub is had passed out to you in the beginning of that, whatever. You guys already have the packet. The packet just has the lines for all these things that we were talking about. The one in your notes packet is the same lesson. It just doesn't have the lines. So I just tried to help you organize your work a little bit. Okay, so now based off of what the graph looks like, let's draw on our graph. It doesn't have to be exact, it's just approximate. So let's look at our graph. So it's going to go ooh, and then down here and up. So it looks something like this. All right, and now that we have this graph, let's answer these questions. So where is the x-intercept? Now, this one is a nice x-intercept. It is at an integer. Not all of them will always be an integer. So the next example we'll do, you'll see we're going to have to trace the x-intercept because there's actually going to be 4 of them, and they're going to be decimals. So this problem is actually a really nice problem. Local max, so that is going to be right here, and we're actually going to have to trace that on our calculator. So let's figure out where that is. So we're going to go, so once you're on the graph, you're going to go second trace, which is going to give us the calc function. We want to trace the maximum, so we're going to hit 4. All right, it's somewhere right here. So left bound just needs you need to get somewhere to the left of it. It doesn't matter how far. And then somewhere to the right bound, somewhere to the right of it. Again, it doesn't matter how far. Hit enter. And then you don't even have to put your cursor over it. All you have to do is hit enter at that point, and your calculator's smart enough to find the local max. So there we go. We can say It's 0.3 repeating, so we can just say 1/3, or we can just say 0.33, and the y value is negative 1.85. And then, like I said, even though technically that local max is at the y value at negative 1.85, we are going to write the point, right? The points where the local max and mins are. So here you can see our x comma y point. Now, obviously my graph, so this little hump that I drew here is obviously not very good because negative 1.85 would be somewhere right here, so it should be much smaller, but I don't really care. You guys are you're just sketching the graph. It doesn't have to be perfect. Okay, local min, let's go trace that. Second trace, now we want minimum, so hit 3. And then left bound, I'm gonna hit enter. Right bound, we need to get somewhere to the right of it, hit enter. And then hit enter again, and your calculator will find the local min. There we go, 0.99. So we can just say 1, and then the y value is negative 2. So the local min is at 1, negative 2. So let's see how good my graph is. 1, negative 2. Yep, that's good. That was one of the points, so that's nice. So there's our local min. Increasing and decreasing. Okay, these are going to be in interval notation. Okay, like I said, we're just talking about the x values, so these are not ordered pairs. So my interval is increasing. So we're going to start, again, we're reading, oops, not negative 8, negative infinity. We're starting from, right, we're reading the x-axis. So we're starting from negative infinity, and I'm going to use a different color. My polynomial is increasing from negative infinity all the way up until the x value of my local max, which is at 0.33. So from negative infinity all the way up to 0.33, my function is increasing. Then it's decreasing from the x value of my local max all the way to the x value of my local min, which is from 0.33 all the way to 1, right? Again, the x value of your local min. And then it's increasing again from the x value of my local min all the way up to positive infinity. So the x value of my local min is 1, and then up to positive infinity. So for your increasing, decreasing intervals, again, you're always talking about the x values, and you're always going to end up using, right? It's always going to start with negative infinity and end with positive infinity, right? Because that's the end behavior here. And then you're always going to use the x values of your local max and min points, because that's where your turning points are, right? Is at the local max and local min points. Okay, let's do another polynomial. This is the last one. It is a little more intense. There's going to be a lot more tracing on the calculator, and then we'll end the lesson with even and odd functions. All right, so let's plug that in our calculator. I'm going to hit clear. So x raised to the 4th power minus 5x raised to the 3rd power plus 2x squared plus 8x minus 2. All right, when you're done, hit graph. Remember, we changed our window, so it might be too small for us. Actually, it is definitely going to be. Ooh, no, it actually looks pretty good. Okay, we can't really see this down here. If we want to zoom out, we can, but for now, actually, we will have to zoom out because we're going to have to trace that. So maybe let's go negative. Actually, I think that one's pretty low. It is, so I'm just going to leave the window where it's at right now. So you can see we have 1, 2, 3, 4 x-intercepts. None of them are at integers except for, actually, no, I don't think any of them are. This one's actually at 4.04. So we're going to have to trace all of those. So how do we do that? Well, actually, first let's let's graph our polynomial first. So let's go to our table and grab some nice points. And you guys can use your graphing calculator to help you graph it as well. All right, so let's make a point at -1, -2, 0, -2, 1, 4, 2, -2, and 4, -2. Yep, those are our nice points. So -1, -2, 0, -2, 1, 4, 2, -2, 4, -2. A lot of -2s there. And then you can use your graphing calculator to help you see the function. We don't really, well, let's look. This is positive leading coefficient with an even degree. So I always relate that to a parabola that's facing up. So that's going to help you with your end behavior. But again, you can already see that on your graphing calculator. So when I graph this, we get something that looks like this. Actually goes down pretty far. There we go. So like I said, you guys can see the end behavior it does match what I think it should match. And you can also see that on your graphing calculator. So we'll see how close we were with our turning points. We'll see. You're just sketching it, so you don't need your local max and mins to be exactly where they're actually at, but by looking at your graphing calculator, you can kind of get a good idea of how to draw your polynomial. Okay, now we're going to have to trace the x-intercept. So I'm going to show you how to do that. So we're going to go second trace again, and then we want to trace our 0. So hit 2. All right, left bound. Well, I'm going to trace this one first. So I need to be on the left side of that intercept. So here, and you use your arrows to go over. So hit enter, and then anywhere right bound, hit enter, and then hit enter again. And our x-intercept is at -1.110. All right, so the first one, -1.110. So yeah, well, ours looks pretty good, right? It does look like it's at -1.11. All right, the next x-intercept. Let's trace the next one. So you're going to have to hit second trace again, and then hit 2. So left bound, so now I'm on the left side of my intercept. Hit enter. Right bound, hit enter, and then hit enter again. 0.24. 0. Yeah, I guess mine kind of looks like it's at 0, but close enough. Right, 0.24 is pretty close to 0. Okay, now I'm going to show you guys, if you don't have a graphing calculator at home, I think most of you do, but if you don't, and actually I kind of like this anyways, if you type in www.desmos.com, it's a graphing calculator. So you're going to hit graphing calculator. You can type in your function. So x and then shift 6 is the caret button. So that's going to raise it to the 4th power. And then arrow down. So it's very similar to how you would plug it in your calculator. Minus 5x raised to the, so shift 6. 3rd power plus 2x squared plus 8x minus 2. All right, so we see the same function. Now, I actually kind of like Desmos because you can just hover your mouse over the intercepts and it already gives you the intercepts. So there we go, -1.11, 0.24, 1.82, and 4.04. So that's pretty nice. It's way quicker than tracing it on your calculator. I don't care if you guys use Desmos at home for your homework, but on a quiz and a test, you guys are going to have to use your graphing calculator because you're not going to be able to use a computer. So you have to know how to trace it on your graphing calculator. So make sure you do some of your homework problems with the graphing calculator so that you know how to do it. And then if you want to do other ones using Desmos because it's a lot quicker, then you can do that as well. So here you can see we have a local min, and then same thing, we don't even have to trace it. Here we have a local max, and then I'm scrolling out, and here we have another local min. There we go. So for purposes of this lesson, let's just use Desmos right now so we don't have to spend 10 minutes tracing everything, but you do need to know how to trace it, right? So make sure you do some of your homework with it, with the graphing calculator. Okay, let's. All right, so you guys saw the third one is 1.82, and then we have 4.04. So 1.8, I think I said 2, and 4.04. All right, let's look. 1.82, yeah, that looks pretty good. 4.04, a little bit past 4. Yeah, all right, our graph's pretty good. All right, local max. So these are local high points, I guess you could say. So I'm gonna, let's see, my local max here is at 1.07, 4.04. Again, we are writing the ordered pair for the local max and local min. So there we go. That's our local max. And then we have two local min values, here and here. So let's use Desmos to find where those are. Negative 0.57 and negative 4.88. And so let's look at our graph. 1, 2, 3, 4. Okay, so I could have gone down a little bit further, but it doesn't matter. It does not have to be exact. All right, this local min is at 3.25 and negative 14.95. I'm going to erase this table just for now so I can write this. All right, 3.25, comma, negative 14.95. Again, we're writing the points for the local max and local min. So there we go. We have one local max and two local min. All right, increasing, decreasing interval. This is very similar, same process that we did last time. Again, for these, remember that it's interval notation. We're talking about the x values. They're not ordered pairs, right? So we're always looking at the x values. So remember, you're always going to start with negative infinity, and you're always going to end with positive infinity. So let's start with negative infinity. When, right, negative infinity is over here. So we come in to the x value of our first local min, and that's decreasing. So it's decreasing from negative infinity to, let's see, the x value of my local min is negative 0.57. Then it's increasing from negative 0.57 all the way up to the x value of my local max, which is at 1.07. Then it's decreasing from that x value of my local max, which is at 1.07, all the way to the x value of my local min, which is at 3.25. And last but not least, it is increasing from that x value of the local min, which we just said was 3.25, all the way up to positive infinity, right? Because positive infinity is out here. I don't care if you guys write the plus sign or not in front of positive infinity. It doesn't matter to me. Okay, so again, remember that we're talking about the x values, so that's interval notation. And like I said, the x values are always going to be the x values of our local min and max. So we started with negative infinity here, we went up to positive infinity, and then all those other values were the x values of my local min and my local max. And that's it for graphing. So again, Desmos can save you a lot of time if you want to use it for your homework at home, or just use your graphing calculator and trace everything, which does take more time. If you're going to trace this one down here, you would have to change your window. You have to zoom out quite a bit, probably more than that. Yeah, well, we know it's at negative 14.95, so you maybe make your y minimum negative 15, and then you'll be able to trace it. Okay, last concept for this lesson is even and odd functions. Essentially, okay, let's just, you guys can read that. I'll just explain it and then it will make sense. Determine whether each function is even, odd, or neither. We're going to do it algebraically. We're not going to verify using our calculator. You can if you want, but I trust you guys doing it algebraically. So what we're going to do is we're going to replace x with negative x. If all of the signs are opposites, then your function is going to be odd. If all of your signs are the same, then your function is going to be even. If it's neither of those, then it's neither even or odd. So I'll show you what I mean by that. So we're going to replace x with a negative x. So this side is just notation. So f of negative x, let's plug in a negative x every place that I see an x. Okay. All right, so negative x cubed means that we're doing negative x times negative x times negative x. Remember that if you're raising it to an odd degree, then it's going to be negative. So negative x cubed is negative x cubed. And then negative 12 times negative x is plus 12x. So if you can see our original function, this was a positive x cubed and now it's a negative x cubed, and this was a negative 12x and now it's a positive 12x. Because all of the signs are opposite signs, that means that it's an odd function. All right, let's do b. So we're going to replace x with a negative x. So we have negative x raised to the 4th power plus negative x raised to the 2nd power minus 7. Okay, when you're taking negative x to the 4th power, you're really doing negative x times negative x times negative x times negative x. But if you remember, if you're raising it to an even degree, then it's going to be positive because it's as if you were squaring something. Right, so it says positive x to the 4th power. Negative x times negative x is positive x squared. And then we just have minus 7 at the end. So look at your signs. Our original function g of x was x to the 4th plus x squared minus 7. And we got the same exact thing, x squared plus x, x to the 4th plus x squared minus 7. So that means that this is an even function because it's the exact same function. All the signs are the same. So the first one, all of our signs were opposite, which makes it odd. In the second one, it was the same exact function, which makes it even. And then in this third example, let's replace x with a negative x. Okay. Again, you're taking a negative x raised to an odd degree, which is going to make it negative x to the 5th. So we originally started with a positive x to the 5th, and now we have a negative x to the 5th, so that's the opposite sign. But we started with plus 9, and we ended with plus 9, so that's not the opposite. So one of the signs is the opposite, and one of them is the same sign, and therefore it's neither. It's not odd or even. So It's only odd if every single sign is the opposite sign, and it's only even if every single sign is the exact same. But in this case, one was the opposite sign and one was the same sign, which makes it neither. And that is it for the lesson today. So you guys have graph paper in your homework packets. It's 4.8. There are, I believe, 6 graphs. There are lines for you to write the increasing and decreasing intervals, and then the local max and local min. And then I think, I can't remember what the directions in the book say, but I think, oh, you also need to identify the x-intercepts as well, so don't forget to do that. I don't think there's lines on your graph paper for that, though. So make sure you identify the x-intercepts. Actually, I don't know. I think I kept updating the graph paper, so I can't remember what graph paper you guys have. So all of the lines might be there. Just make sure you answer every question. X-intercepts, increasing, decreasing, local max, local min, and then your table to help you graph the function. Okay, if you have any questions, email me, and I will see you guys tomorrow, either online or in person.